Hey everyone, I am Dr. Surjit Singh. In this video on Python via examples, we shall talk about the merge sort method. Let us begin. In this session, we will learn about merge sort. This is a stable sort. We shall deal it as both top-down and bottom-up approaches and discuss their time and space complexities that we will compare with other methods. For stable sort, merge sort is the best. This follows the divide and conquer approach. We will first discuss it as the recursive top-down approach. We are given a list for sorting. We pass it as a parameter to the function merge sort, which is a recursive function. This will use merge function that we will develop later on. We do not need any sorting if list has only one item or if it is empty. This becomes the edge case for the recursive function merge sort. In this divide and conquer approach, we find the index of the middle item of the list. Length of the list is 10, so mid becomes 5. This divides the list into two parts. We copy left part of the list that contains the items before mid of the list. We call it left. We copy the remaining part of the list from mid onwards in another list that we name as right. We do not need the original list now, so let us clear its memory. Firstly, we sort the left list and then the right list using the same function merge sort that we are developing now. This style of argument is common in all recursive methods. After we establish that merge sort works for the bigger list, that is A, of 10 items, it will also sort two lists of 5 items. So we assume here that it works for the two sublists left and right. Last step is the merging of left and right lists back into list A. We call the function merge, in which the parameters left and right become x and y. Let us now develop the merge function. List A is the parameter of the holding function, so we declare it here as non-local. This enables us to modify the list A, and we will merge lists x and y in this list A. We run a loop while neither of the lists x and y is empty. We compare the starting items of both of them, pop out the smaller of the two, that is 0 of y, and append it to A. In the next iteration, 1 is less than 4. We pop out 1 from x and append it to A. Next two iterations will process 1 of x and 3 of x. When both the items are equal, we process list x and append 4 to A after popping it out. This ensures that merge sort is stable. Two more iterations process 4 of y each time. This is followed by 6 of x. With this, one of the lists is empty, so we come out of the while loop and append the residual parts of x and y to A. Sorting of list A is over. Let us now quickly dry run all the recursions of this sorting. We divide the original list as left and right. This takes extra memory of the order of n, though for a short time. In the next step, we release the memory of the original list. In order to sort the left part, we split it again and then clear it. We split the list 3, 1 further into 2 and then clear it. Both of these lists 3 and 1 are of length 1 each, so both are edge cases. We merge them into their parent list by moving first the smaller of the two, which is 1, and then moving 3. We now sort its right part, that is 6, 4, 1, by splitting it. 6 is the edge case list, so we now split 4, 1. Both 4 and 1 are edge cases, so we merge them to their parent. Both 6 and 1, 4 are now sorted lists, so we merge them to their parent. We have separately sorted both of the lists 1, 3 and 1, 4, 6, so we start merging them. Both sides have 1, so we move the item of X list first and move 1 to its parent list. After that, we move 1 of Y and then 3 of X. One list is now empty and we append the other to the parent. We have now sorted the left list, so we split the right list and clear it. Further steps are as shown. We have now sorted both left and right. We will now merge them. The list is now sorted. Let us now view all the divisions of the original list. Height of this tree is log of n. At each level of the tree, we process n items. Processing of each item takes constant time. So time complexity is n for each level. Therefore, for log n levels, the total time complexity is n log n. For splitting the lists, we need extra space of the order of n, but we have to copy the lists in each recursive call. So the total additional space that we use is of the order of n log n. Moreover, the call stack of recursion will have at most log n entries for which we need log n additional memory to maintain the call stack, but it is negligible compared to n log n. Let us now discuss the bottom-up approach for merge sort. This has to be an iterative method. We begin with an overview of this method. In the first iteration, we sort the consecutive pairs of items of the list to get this list. In the next iteration, we merge the consecutive pairs of segments of width 2 each by sorting them while we leave the unpaired segments as such. We double the width of the segments in each iteration. In the next iteration, we merge and sort the pairs of segments of width 4. Resulting list has sorted segments of width 8. Process continues. We take care that right segment can sometimes be of shorter length. Sorting is now complete. With this algorithm in mind, let us write the program for this. N is the length of the list. Starting with 1, we shall change width in a loop while it is less than n. Start is the beginning of the 2 items that we will sort. It varies in a loop from 0 to the end of the list. Increment is of 2 widths each time because we sort the pairs of items in each iteration. In the first iteration, we sort the pair 3, 1. 3 is the left segment. Mid of interval is at start plus width. Left segment ends before mid from where the right segment starts. In a case where mid is outside the list, the right segment would not be present and no merging is required. In that case, we will break this loop. In the present case, we proceed further. End is mid plus width. Right sublist finishes before end of the interval. We have used the min function to ensure that end is not greater than n. We now carry out merging and sorting of left and right segments in a function that we will discuss shortly. This merging will result in a single sorted segment 1, 3. In the next iteration, we increase start by 2 times the width where we sort 6 and 4. When start is 4, we process 1, 4 even when they are already in order, and then start becomes 6. We set the order of 0 and 8. Finally, start becomes 8. We sort 4 and 7. With this, the for loop ends. We have now set up sorted segments of A of length 2 each. Therefore, in the next iteration, merging of segments will be of double width. When start is 0, left segment is before mid, that is 1, 3, and right segment is before end, that is 4, 6. We have already sorted both left and right individually in the previous iteration. We will now merge them with each other to get a sorted segment of 4 items. By chance, 1, 3, 4 and 6 were already sorted. Next value of start is 4. We now merge 1, 4 with 0, 8 to get a sorted segment of 4 items. When start becomes 8, mid becomes 10, which is outside the list, so we break the loop here. Note that right part is missing and we do not have to merge segments of list A. In the next iteration, width becomes 4. Both left and right segments are of 4 sorted items each. Merging them gives a segment of 8 sorted items. For start equal to 8, mid is outside the list. So there is only left segment of 4 and 7 while the right segment is missing. So we break this loop. Width now becomes 8. Start is 0 and mid becomes 8. Mid plus width is much more than n, but we keep n to be n. We merge the two lists of length 8 and 2 items to get the final sorted list of 10 items. We shall now write the merge function. Sample values for the discussion are taken in which start, mid and end are 4, 6 and 8. We copy the left and the right slices of A in new memories. We set pos equal to start. We run a loop while neither left nor right is empty. We compare their starting items, pop out the smaller of the two and paste it in the list A at pos. We increase pos by 1. In the next iteration, item of left is smaller. We pop it out and put it at pos. Pos moves further. In the next iteration, we pop out 4 and save it as pos. Pos moves to the next position. With this, left is empty, so we come out of the loop. One by one, we copy all the pending elements of left, if any, and then the elements of right. With this, the merging of left and right is over. We use the same function in all the merging of segments of list A. Number of times we change width in a loop is the height of the tree, which is log n. For each width, we process the items n times. So time complexity is of the order of n log n. Copying of the left and right segments uses extra memory at most equal to n. So the space complexity is of the order of n. In bottom-up approach, there is no call stack involved, so it uses lesser memory than the recursive top-down method. We will now compare merge sort with other sorting methods. It is clear that merge sort is much faster than other methods. However, some overheads dominate if n is less than 60. Best stable sort methods use merge sort that shifts to insertion sort when in an iteration size of a segment goes below 60. In this session, we discussed the top-down method in which we recursively split the list to left and right halves from the middle, separately sort them recursively, and then merge them again. In bottom-up method, we sort and merge the adjacent sublists and doubling their widths in each iteration. We discussed their time and space complexities and compared them with some other methods. Hope you enjoyed the video. Please feel free to ask for further clarifications on my email address given below. I'm looking forward to your comments. Please stay tuned for more such videos.